Okay, the next part of sequences that we're going to look at is something called convergence and divergence. I mentioned this very briefly one day, but I'm going to go into it in more detail here. This actually goes back to the very first section of this chapter. I just kind of skipped this part of it. Um, a sequence, if you remember, is simply an ordered list of numbers where it's represented by a function, and to get the individual terms, you just plug in positive integers. So I start by plugging in 1, 2, 3, and you write out the terms of the sequence. So this is what a sequence is, which you hopefully know that. With convergence and divergence, a sequence converges if its terms, as you keep writing your terms forever, if the terms approach a specific number or value as n approaches infinity. A sequence diverges if your terms do not approach a specific number or value as you plug in larger and larger numbers for n. Some examples of convergent sequences are right here. There's my pen. Why isn't it working right? Hey, come on, work with me. Here we go. Um, Here's one sequence, 1 over n plus 1. And what I've done here is I've written out a bunch of terms. I started by plugging in 1. So here's n equals 1. Here's n equals 2. So on and so forth. Here I've gotten all the way down to where n equals 99. And I skipped a bunch. This is n equals 100. And then I skipped a whole bunch. And then I went all the way on and I plugged in right here. This is n equals 2659. And what I've done is I've written out a whole bunch of terms. And if you look at those terms, hopefully you can tell that those fractions are getting smaller and smaller and smaller and smaller. If you were to punch in 1 divided by 2660 in the calculator, you would get a decimal of 0.00038. So this thing is pretty close to 0.00038. And if you look at those, you can see that hopefully these fractions, we started out at 1/2, which is 0.5, then 0.3, 0.5, 0.3 repeated, 0.25, 0.2. This is 0.01. As you go further and further to the right, these decimals are getting closer and closer to 0. So this one, we would say converges. My writing is terrible because I have a huge band-aid on my thumb. Oh well, that says converges to 0. So this sequence does converge. This one, if I start plugging in numbers, we start with 1/6, which is 0.16 repeated, 2/7, which is approximately 0.28. 0.2, I'll say, yeah, that's right, 0.28. 3/8 is 0.1, no, it's not, it's 0.375. 4/9 is 0.4 repeated. And as we keep going, here I've plugged in, this is when n is equal to 1001. If I plug 1001 divided by 1006 in the calculator, you get a decimal of 0.995. And what's happening here is these decimals, as you keep going to the right, these decimals are converging to 1. They're getting very close to 1. As you keep plugging in larger numbers for n, your terms are getting closer and closer to 1. A few examples of divergent series, and these are a little bit easier to see. Here's the first one. This is an arithmetic sequence, 3n plus 2. And as you start plugging in, this is when n equals 1, this is when n equals 2, and then I skipped on. This one I think is when n equals 2000. This one right here is when n equals 2001. As you go on and on and on, you can see that these numbers are just getting larger and larger and larger, and they will continue to get larger because I'm adding 3 each time. So this one diverges. So it doesn't diverge to anything, it just diverges. Numbers keep getting bigger and bigger. Number 2 is a geometric sequence. And this geometric sequence will diverge also, because if you write out the terms, you'll see that they are doubling and they're changing signs. I'm going from -6 to +12 to -24 to +48. And these numbers just keep getting larger and larger and larger. And so this one diverges also. A little note, all arithmetic sequences will diverge. All arithmetic sequences diverge. Geometric sequences, it depends on what the ratio is. The geometric sequence will actually converge if your ratio is between -1 and 1. It will diverge if your ratio is above 1 or less than -1. So that is what a convergent and divergent sequence is. The ways you can test for convergence is you could do exactly what I just did, where you just write out a whole bunch of terms and see if it looks like they approach a particular number, and you can punch in your calculator to see if they do approach a particular number. That's not really smiled upon by the Math League of America. If the representative from the Math League of America was here teaching this class, they would say that in order to determine if a sequence converges, you actually go into limits. And you may have noticed some of the language I was using earlier. I used the word approaches. I said as n approaches infinity. You actually do prove these things with limits. And the way you would do that is you simply take the limit of the sequence. If the limit of the sequence actually equals a number, then your sequence will converge. So let's go back and look at these things, the two that converged. If I did do the limit as n approaches infinity of 1 over n plus 1, this is an infinite limit. N is approaching infinity. My bottom degree is bigger than the top. That means this limit equals 0, and that's actually what the series converged to. So that's one way, if you're good with limits, if y'all remember that limit chapter, that's one way you can actually determine whether or not these sequences converge. Same thing for number 2 here. If I did the limit as n approaches infinity of this, n over n plus 5, it's an infinite limit. We have a rational function, so the top degree equals the bottom degree, which means we would divide the coefficients, and 1 divided by 1 is 1, and that's actually what the sequence converged to. So one way you could test for convergence is to do a limit. Now limits get a little bit trickier when they diverge, and sometimes the calculus required to do limits is too tricky, and we'll just have to write out all the terms. So I have 4 examples. We're going to determine whether or not these sequences converge. And if they do converge, I want to say, let's say it converges to 3 or to 7 or something like that. Uh, let's do this one the less mathy way. Let's just write out some terms. I'll plug in 1 for n. 1 minus 3 is negative 2. 1 plus 2 is 3. My next term would be 2 minus 3 is negative 1. 2 plus 2 is 4. My next term, 3 minus 3 is 0. 3 plus 2 is 5. And eventually you'll start to see a pattern. My numerator and denominator are both going up by 1. So it's going to be 1 6, 2 sevenths, 3 eighths. And early on in your sequence, it may be hard to tell what's going on. So we really don't need to know what's happening in the first 5 or 6 terms. We need to know what's happening way out here when n is something big, like 1,000. If I plug in 1,000 minus 3 is 997, and 1,000 plus 2 is 1,002. If I plug in 1,001, you get 998 over 1,003. And if you plug those fractions in, 998 divided by 1,003, you will get 0.995. And what's happening is these decimals, at the beginning they start kind of weird. We actually hit 0, and then we have 1,627. But as I work out towards infinity, as my n's get larger and larger, these things are converging to 1. 0.995 is really close to 1, so this converges to 1. Now the more mathy way you could do this is the limit. I could do the limit as n approaches infinity of n minus 3 over n plus 2. It is a rational function. Top degree is equal to bottom degree, so I will divide the coefficients, and 1 divided by 1 is 1. So we could do the limit. We could also write out all the terms, and I'm perfectly okay with using either method. Number 2, if you wrote out all the terms, if I plugged in 1 for n, 3 minus 2 times 1 is 1. 3 minus 2 times 2 will be 3 minus 4 is negative 1. 2 times 3 is 6. 3 minus 6 is negative 3. Plug in 4. 3 minus 2 times 4 is 8. 3 minus 8 is negative 5. And I see my pattern. I'm subtracting 2 each time. Negative 9, negative 11. And if I skipped some and plugged in a huge number, if I plugged in something like 1,000, if I plugged in 1,000, let's see, 3 minus 2,000 would be negative 1,097. And what's happening here is this thing is just blowing up. So this one diverges. Also, hopefully, you recognize this as an arithmetic sequence because this is in slope-intercept form. You could say this is arithmetic, therefore it will diverge. All arithmetic sequences do diverge. If you tried the limit way, the limit as n approaches infinity of 3 minus 2n, it's not a fraction. I like when my infinite limits are fractions because then you could look at top and bottom degrees. So to turn this into a fraction, I will just put this over 1. And in this case, my top degree is bigger than the bottom degree. My top degree is bigger than the bottom degree. And if the top degree is bigger than the bottom degree, we said that in that case, the limit does not exist, which is why the sequence diverges. Um, Technically, this thing approaches negative infinity because my top is going towards a huge negative number, which we showed up here earlier with negative 1,097. Not whatever, 1,997. All right, so there are two ways you could do this. You could write out the terms and see that they just get bigger and negative, or you could do the limit. Two more. This one, 5 to the n, or 5 times n over 5 to the n power. If I plug in 1 for n, 5 times 1 is 5. 5 to the first power is also 5. If I plug in 2 for n, 5 times 2 is 10. 5 squared is 25. If I plug in 3 for n, 5 times 3 is 15. 5 to the third power is 125. If I plug in 4 for n, 5 times 4 is 20. 5 to the fourth power is 625. And then we could skip a few terms. And this one, we have what's called an exponential function down here. We have talked about exponential functions in the past, but it was a long time ago, so you probably forgot. But exponential functions get big in a hurry. If I try to plug in 1,000, I'm going to plug it in real quick. 5 to the 1,000 ends up being, holy cow, I knew it was going to be massive. In the last few problems, I tried plugging in 1,000. The problem with 5 to the 1,000 is it ends up being 9.3 times 10 to the 698th power. So if I wanted to write this thing out, I would have to move the decimal to the right 698 terms. That is some massive number that I don't even know what to call it. So with exponential functions, we really don't need to plug in huge numbers. I could probably just plug in something like 10. 5 times 10 is 50, but 5 to the 10th power, which is still going to be a massive number, 5 to the 10th power is 9,765,000. And 625. And it goes on. And if I were to punch that in the calculator, 50 divided by that 9 million number, you will get point, this thing is equal to 0.000005. That's pretty darn tootin' close to 0. So this one we will say converges to 0. Because my terms, my decimals are getting so close to 0 that that's what this is going to converge to. Where's my 0? There it is, or my O. All right, so this one does converge to 0. As far as the limit, if you tried to do the limit of this one, and this is why I was kind of hesitant to show you the limit technique, because it really only works when you have a nice rational function. This technically is not considered rational, even though it is a fraction. A rational function works best with polynomials, and 5 to the n, you don't have a degree for that. So we can't really do this. I'll say you can't do this yet. At some point in your lives, if you take a higher level calculus, you will learn how to do that limit. You use something called L'Hopital's rule, and you have to use derivatives and all this mess. So we can't do this one yet. So sometimes the limit's not going to work, in which case it's easier just to write out the terms.